So in the last class, we studied filters. Uh, we studied passive second order filters. And today we are going to study the active implementation of those filters. But before we go into the active implementation of the second order filter, first we will revisit the first order filter once again. But this time we will see that how to do the non-inverting implementation of first order active filter. Recall that the active filter first order circuit that we discussed in the previous classes, they were for inverting mode. So we will discuss non-inverting first order active filter, then we will go on to discuss second order active filter. And if you recall the previous lecture, then the second order filter were implemented using RLC, and it was pointed out that L is typically avoided in integrated circuit because it requires a lot of area. So what we will do today is we will study a circuit called simulated inductor proposed by Antonio. So this circuit consists of RC and op-amp, and we will see that this circuit behaves like an inductor, although it does not contain any inductor. So we will use this circuit and revisit the high pass and band pass filters using RLC. And in these two circuits, we will substitute the inductor by this simulated inductor. So we'll see that although the simulated inductor circuit size is big in terms of number of components used, still when fabricated in IC technology, it will acquire significantly small area compared with conventional inductor fabricated using the same technology. And then we will see that how to implement low pass filter without using inductor. And we will see that it will not be possible to use this simulated inductor in a straight way, direct way in the low pass filter circuit that we discussed in the last class using RLC. And we will see that we will have to do modification in this circuit to arrive at a new circuit which then can be used to implement low pass filter, but not in a straight way as we will be able to do the band pass and high pass cases. So first order active low pass filter, but now in the non-inverting mode. That means input will be ultimately connected to the non-inverting terminal of the op-amp, and the output and input, they will be in the same phase. So we have already seen that first order passive low pass filter is given by this circuit, RC circuit, simple RC circuit. And then what we can do, we can take a simply unity gain amplifier. That means short circuit the output to the negative terminal, and then simply cascade these two circuits. That means we simply connect the output of passive circuit to the op-amp, and that will give rise to this circuit, whose transfer function here you can see is of first order, and that to low pass filter, with of course DC gain is equal to 1. So this one is very straightforward implementation of first order active filter in non-inverting mode. And since the gain is equal to 1 at DC, so one might ask that what is the utility of then adding this op-amp here if we are not getting any gain? Then why shouldn't we simply stop at this passive circuit, this one? So there's one added advantage of adding this op-amp, and that advantage is to eliminate the loading effect. So for example, if we decide to use only this one and then we connect it to a load, then in this case output will of course be not given by this transfer function. So in this case, we can see that V out by V in, this will become parallel of ZL parallel with uh, this capacitor C divided by R plus ZL parallel with C. So here you can see that this transfer function in general will not be same as this one, what we have obtained after putting this op amp, or what we obtain when ZL is infinite, right? So the advantage of putting this op amp is not only to possibly have a gain at DC, but this also offers advantage, at least in this circuit, that it will eliminate the loading effect. So now here, even if I connect a load of whatever value, the transfer function is going to be this one. This transfer function is not going to get affected, right? So this is the advantage of another advantage of putting op amp, or alternatively going for the active first order low pass filter. So here we had a DC gain is equal to 1, but if someone wants gain also, then it's relatively simple to modify this circuit. We just need to modify this negative feedback path, and then one can add these two resistors R2 and R3 and start with non-inverting amplifier with certain finite gain. And we know that here gain will be given by 1 plus R2 by R3. So now instead of taking unity buffer, we take finite gain amplifier, and we take our usual passive low pass circuit, and then what we do is we simply cascade them. So when we cascade, this is what we get. So transfer function simply gets modified, and here what we are getting is the previous transfer function. So new transfer function you can say is the gain R2 divided by R3 into the transfer function that we had got for unity gain, the previous gain. So the final transfer function derivation is also straightforward, simply product of two cases. And the loading effect advantage remains here valid also. That means you can connect ZL, and the transfer function remains this one. But here we see that it will get modified for the passive case. Now we come to main circuit. That means we wanted a second order active filter. And so first we will consider second order low pass active filter. And uh, since op amp is going to be used, and we know that op amp can be fed either at the plus terminal or the minus terminal, so there will be typically two versions, but we are going to discuss non-inverting case, and we will keep the thing simple. We are going to consider unity gain case, but let me warn you that unlike the previous case, the first order filter case, here when you move from unity gain to finite gain case, situation is significantly more difficult. It's not the straightforward transition from unity to finite gain case like we saw for the first order case. So that is why here we are keeping the thing simple. Okay, so actually there are a few circuits of second order active low pass filter, and one of them, the most popular one, was proposed by Sallen-Key, and that is why this circuit is called Sallen-Key low pass filter. And there are a few others also which we will see in future classes. And here you might also have noted, or let me emphasize, that we are always considering a low pass filter. The first order circuit that we just now consider, or even in previous class, they were low pass, and second order circuit that we are also considering is low pass. And the reason will be explained that once we have a low pass filter, it can be easily transformed to high pass, band pass, or other type of circuit. So that is why we will be focusing only on the low pass version of the filter. So here we have this Sallen-Key second order active low pass filter with DC gain is equal to 1. So here we have this negative feedback. So this is responsible for DC gain is equal to 1. And now you can see that we have two capacitors, which is typically the scenario encountered in second order circuits. There will be two storage elements, but there could be more also, and even with two, one can get a single order. So it's not a direct relation that two will always imply second order. So here you can see that we have this circuit where we have input connected to finally to the non-inverting mode of the amplifier, and first objective for this circuit will be to find out the transfer function. That means we need to find out VO by V in. So what we will do, we will have to set a few equations. So we start with the finding out the voltage at node X and node Y, and then we will try to relate output with the input. So here what we have is negative feedback is there. That means output is connected to the inverting terminal. So negative feedback is present here. This will imply virtual short between plus terminal and negative terminal of the op amp, right? So here what we will get is, so when we apply this virtual short condition at node X, this implies that Vx is equal to V out. So this is the equation 1 that we obtained from this case. Now we will try to find out voltage at node Y. So to find voltage at node Y, we will have to apply KCL at node X. So at node X, we will apply KCL. So here you can see that by the definition of ideal op amp, this current I plus is going to be 0. That means whatever current comes to node X, it goes to ground via capacitor C2. So when we apply KCL at node X, what we get is Vy minus Vx divided by R2 is equal to current through the capacitor C2. So that is going to be Vx divided by the reactance of capacitor C2, which is 1 by S C2, right? So this gives rise to Vy minus Vx divided by R2 is equal to SC2 Vx. But from equation 1, we already know that Vx is equal to V out. So this implies Vy minus V out by R2 is equal to SC2 V out. So we can replace or eliminate Vx from the equation. So now here we can separate out Vy and V out. So when we do that, we get this thing, Vy is equal to V out into 1 plus R2 C2 S. So this is equation 2. So now we know the value of node X voltage and node Y voltage. These two quantities are known to us now. So we have to finally find relation between output and input. So for that, we will do what we will do is we will apply KCL at node Y. So here we have three currents moving away from node Y. This is say I1, this is say I2, and this is I3. So there are three currents, I1 plus I2 plus I3 moving away from node Y. So we now substitute each of the currents, Vy minus V in divided by R1 plus, see this I3 will ultimately flow through the capacitor C2 because current into op amp is 0. So what we do is we write this I3 in terms of capacitor C2. That means, and Vx we have already seen is equal to V out. So this is Vx by 1 by S C2, and I3 is sorry, this is I3. I made a mistake. This is I3, and I2 I'm going to write here, which is Vy minus V out divided by 1 by S C1. So here this becomes Vy minus V in by R1 plus Vx is V out into SC2 plus Vy minus V out into SC1 is equal to 0. So here what we have is unknown Y appearing in this equation. So this unknown Y can be eliminated from equation 2, which we obtained earlier. So from equation 2, if we eliminate Y, what we will get is this equation, V out into 1 plus R2C2S minus V in divided by R1 plus V out SC2 plus V out 1 plus R2C2S minus V out into C1 S is equal to 0. So from here we can find out V out by V in, which will be the transfer function that we are looking for. So when we do this manipulation, what we get is this equation, R1, R2, C1, C2, S square plus R1 plus R2, C2S plus 1. So here you can see that we have second order denominator and numerator is constant equal to 1. So this gives rise to a second order transfer function, that circuit, and that too of low pass type because the numerator is 0th order, right? So this is the transfer function we have derived. And we can write it in the standard form. That means coefficient of S square as 1, and then we can compare with the standard form that we saw in one of the classes, in fact the last class, that is gamma divided by S square plus S omega n by Q plus omega n square. So now we can compare this standard transfer function with this one to find out the various values of the omega n and Q. So when we do this comparison, omega n can be obtained by comparing this with this one, And here you can see that omega n will turn out to be 1 by square root of R1, R2, R3, R4, sorry, C1, C2, R1, R2, C1, C2. So this is what we obtained, Q and omega 1, and DC gain you can see is equal to 1 because we had started with a unity gain mode of the op amp. Now what we would like to do is modify the circuit so that we can get finite gain also. So in that case, modification leads us to this circuit where we have R3 and R4 in the negative feedback. Right? So here we cannot obtain the transfer function of this case by multiplying the transfer function of the unity gain case by factor R3 by R4. So here the transfer function, this cannot be written in this form. So what we obtained earlier. So let me call this as unity gain case. So this conclusion is wrong. And to give you some idea that why this conclusion is wrong is because now output is also connected to the input side through C1. So if it were not, if this side had been completely isolated from the output, then we could have obtained the overall transfer function using this equation. But since it is not, so this equation is no longer valid here. So we will have to carry out the fresh derivation. So here all those steps that we took, they all are going to be valid. And the modification that will occur here is in terms of Vx. So now from virtual short, the Vx voltage is going to be equal to this V minus voltage, and this V minus voltage is now going to be R4 divided by R4 plus R3 into V out. So this is the modification that will occur. So now we have this additional term 1 divided by 1 plus R3 by R4. So this will slightly complicate or the derivation of the transfer function. So if you repeat all the previous steps, key step, that means now KCL at node X, KCL, so KCL at X, then KCL at Y. So what you will get is finally the transfer function, and that transfer function will now be given by this expression here. So I pointed out that the transfer function will not be the product of gain of the op amp and the older transfer function. And here you can see that although numerator has that product, but in the denominator you can see that ratio R3 by R4 appears. So that is why this is not simply the product of the two transfer functions. And here also one can divide numerator and denominator by this factor, and then compare with gamma divided by s square plus omega n by qs plus omega n square to find out the natural frequency and quality factor. So natural frequency here also remains same, but the quality factor now you can see that it gets modified by this factor. And the DC gain obviously is now 1 plus R3 by R4. So this circuit will not only do the low pass filtering, but it will also do the amplification of the passband signal. So from the transfer function, we are convinced that this is going to be of low pass type, but now let us qualitatively try to uh, analyze this circuit at the two extreme values of the omega. That means omega small and omega high, very high in fact, to see that indeed it suppresses the high frequency components. So the equivalent circuit of the Sallen-Key circuit at the small omega will be given by this, where the capacitors C1 and C2, they will be open circuited. So now here you can see that the output has got isolated from this input side. So in this case, this circuit transfer function can be found out product of this much transfer function and that of the non-inverting amplifier. But here you can see that since the current into op amp is 0 and this current, which was earlier called I2, is also 0. So whatever current flows, it flows to both. In fact, there will be no current because this path is also broken, right? So what happens here is Vx will be simply equal to V in. So that means we will have simply this circuit, which is non-inverting amplifier. And we know that in this case, the output and input, they are related by this equation. So, and this is what we concluded from the transfer function also, that means gain at the DC or at low frequencies given by this. Now at high frequency, what will happen is the capacitors, they will be short circuited. So now you can see that what we have here is this scenario. So here Vx is equal to 0 and we have this negative feedback. So it says that this part is also going to be 0. Right? So this is basically, you can say this portion is fundamentally a non-inverting amplifier whose input is 0. So that implies that since Vx is 0, so this will imply that V out is also equal to 0. So when the frequency is very high, in that case, we see that the output will be 0. Actually, in real life, there will be small output, but that will be smaller than the input. So this circuit, what it does is it suppresses or attenuates the high frequency component. So that is why this one will act like low pass filter. So what we had is second order low pass filter. Now we would like to implement second order high pass filter and second order band pass filter, right? So we have already seen RLC version of high pass and band pass, and in that case inductor was there. Inductor now needs to be substituted by some other circuit. So what we will do is we will now study a circuit which is called simulated inductor, because we will see that it will behave as inductor if suitable values of R and C are selected in the circuit location. And moreover, it will behave like a grounded inductor. So what do we mean by grounded inductor is one of the terminals is grounded. So this is where we can connect it to circuit, other will be grounded. And we will see that this simulated inductor cannot be used for floating inductor scenario. So this cannot be realized using this simulated inductor, only this can be realized. So in RLC circuit, we can substitute this grounded inductor by this simulated inductor to simply convert the circuit into second order active high pass or band pass filters. Low pass, anyway, we have studied, but we'll revisit RLC based low pass also. So this is the circuit of Antonio inductor or simulated inductor. So here you can see that we have two op amps, A1 and A2, and there are five impedances, Z1, Z2, Z3, Z5. And as was pointed out, this is used for implementing the simulated inductor. That means this much portion will be equivalent to an inductor. Here. This end is grounded. So our first objective will be to find out this Z in, and then we will try to see that under which condition of these impedances this circuit behaves like an inductor. That means the impedance is going to be of form L omega, and it will be of course positive. This type of impedance will be obtained. So we will carry out the analysis of this. So here so first we will try to write equation for current through Z1. So which will be Vx minus V2 by Z1 will be the current through Z1, which is also equal to Ix. Because we know that this current I plus is going to be equal to 0. So entire Ix will flow through Z1. Right. So this is equation 1 that we obtained. Now we have to find out equation for V2 because unknown quantity here is V2, and to find out Z in we basically need to find out Vx by Ix. So we have to set up equation for V2. So for that what we do is we try to write the equation through current through Z2 and Z3, because although at this junction node 3 there are 4 paths, the current into op amp is going to be 0. So out of these 4 paths, 2 paths are going to be of no importance, and whatever current flows through Z2, the same current will flow through Z3 also. Right. So we are now going to write basically KCL at node 3. So this current I2 is going to be equal to current I3. So what we get is V2 minus V3 by Z2 is equal to V3 minus V4 by Z3. Right. Now here, since these op amps, they have negative feedback. Here you can see that the output of this op amp is ultimately connected to negative terminal. Similarly, the output of this negative terminal is also connected to the negative terminal for this op amp. So that means virtual short will be applicable for both A1 and A2. So virtual short is applicable for both the op amps. So that will imply that the voltage of this node V1 and V3, they are equal. Similarly, the voltage of V3 and V5, they are equal. Right. So virtual short implies V1 is equal to V3 equal to V5, and this V1 is equal to Vx. So V5 is also equal to Vx, and of course V3 also. So what we can do is now we can substitute this V3 using this equation. So this previous one, this becomes V2 minus Vx by Z2 is equal to Vx minus V4 by Z3. So we have been able to eliminate V3. Now we need to tackle this V4. And now you see that what happens here is current through Z4 will be same as current through Z5, because again the current into op amp, this current is 0. So whatever current goes into Z4, the same current goes through Z5. So using this, we can write equation for Z4. So that means we are basically writing KCL at node 5. So that will give us V4 minus Vx, which is V5, divided by Z4 is equal to Vx divided by Z5. Right. So we have here equation 1, and then we have equation say 2 here, and then here we have equation 3. Right. So here you can see that in equation 2, the unknown V4 appears on the right side, and in equation 3, unknown voltage V4 appears on the left side. So we can multiply equation 2 and 3. You can do the multiplication so that this V4 gets eliminated, and we will have only V2 and Vx left out. Right. So equation 2 into 3, that will imply V2 minus Vx is equal to minus Z2 by Z5 Z4 by Z3 into Vx. So this is what we will get. So this is equation 4. Now this V2 can be eliminated using equation 1, which has V2. So this part we have already done. So finally, when we eliminate what we will get is Ix is equal to Z2, Z4 divided by Z1, Z3, Z5 into Vx. So this is not 5, but this is going to be actually 4. So from here we find that Zin is Vx by Ix is equal to Z1, Z3, Z2, Z4 into Z5. So the input impedance will be dependent upon all the 5 impedances in this fashion. Right. So what we want is, we want this to be of this form, say certain constant k into s, or j omega into k, and this k, and this should be positive, so that we can say that this behaves like an inductor. So what we will have to do is make suitable choices for all these 5 impedances. So suppose we make this choice that we take Z5 is equal to Rx, a resistor. Z3, Z4, Z1 also register, but of certain different value. But Z2 capacitor, right? So what we have done is Z2 has been substituted by capacitor, but Z1, Z3, Z4, and Z5, they all are registered, right? So if we make this choice, then what we get is the input impedance. Here you can see that is given by this expression. So that means J, Rx, Ry, C, omega, right? And we know that for inductor, the reactance is given by J L omega. So here you can see that we have an inductor L whose value L is given by Rx, Ry, and C. So there is no inductor, yet this behaves like an inductor whose other end is grounded. So keep in mind that this is grounded inductor. So that means now if you have any circuit where grounded inductor exists, you can simply substitute that inductor by this big circuit. So as I pointed out, this circuit is big, and if you see the internal circuitry of op-amp, there will be more than 20 transistors. So here we have 20 transistors, here we have 20 transistors, and in addition to that, we have these resistors and capacitors. So the number of component count is of course here very high, and here we have only one inductor, one component, and here we will have sort of 50 components. Yet the area required to fabricate this in IC technology is going to be much less compared with the area required to fabricate one inductor. So that is why we will be using this inductor wherever we encounter grounded inductor. So that was one of the ways in which Antonio circuit can be used as inductor. And there's another choice that can be made for those impedances to have inductor, and this is when we take Z4 as capacitor and the rest of the impedances as resistors. So here we have 1, 2, 3 resistor, Z4 as capacitor. So in this case also we have inductor, but now the inductance value is different. So here L is now equal to Rx Ry square into C. Earlier we had Rx, Ry, and C. Right. So this is alternate implementation of the inductor, but topology is same. Now we return back to our high pass case of second order. So we saw that this circuit is a second order high pass circuit, and here we have a grounded inductor. So that means we can simply take Antonio circuit and connect here, and this circuit will still be high pass filter, and area will also be smaller compared with the this one.
So
Yes.
So can you go upper slide in this next one, previous one? Sir, why there is Ry square? Shouldn't it be Ry? Because in division there will also one Z2 which is also Ry.
One by CS. Yes, so here also we will have same thing. Yes, we're right. So there is a mistake here, and it will be Ry. So here also we get the same expression. Right. So it is not Ry square, but it is simply Ry. And in this case also, inductor is Rx, Ry, and C, like the previous case. Okay, so Antonio inductor not only can be used for high pass, but it can also be used for band pass, because recall that for band pass, the circuit that we had was like this. So for band pass filter also we have grounded inductor. So here again this inductor can be replaced by this. But for the low pass case, here is the low pass, and here you can see that we have a what is called floating inductor. That means none of the terminals is grounded. So in this case, we cannot use Antonio inductor to substitute this L, because here uh, what we had done earlier is we had grounded this one. So if you directly try to connect this Q to this Q and this P to here to replace this inductor, this circuit is not going to work. So for that, what we will do, we will see that what is the impedance that C from looking from Q towards this, because when this circuit is going to be substituted here in place of inductor, this will be driven by V in, right? So, and we have to see that from Q point, it should behave like inductor. Then only this substitution will be valid. So our objective now is to find out what is the impedance looking into this circuit from node Q, where it is being driven by an external input. So we have to now find out what is the equivalent Thevenin model of this complete setup. So we have to find out Z Thevenin and V Thevenin. So here finding out V Thevenin is simpler, because we know that from virtual short, this node and this node, they are going to be of same voltage. So this is V in, so this is also V in. Now this node and this node, they are also going to be same voltage, so this is V in. And for finding out Thevenin, we keep this output port open, so there is no current through this Rx. That means this Z in is also, sorry, this voltage that we will see here is also going to be V in. So Thevenin voltage is going to be same as V in. Now we have to find out Z Thevenin. So for finding out Z Thevenin, what we will do, we will short circuit the external voltage source. So we ground it, and then we connect external unknown voltage here, find out Ix, and ratio of these two is going to give rise to the Thevenin uh, resistance. So from here we see that again from virtual short, this is 0 volt, this is 0 volt. That means this Ix will be simply equal to Vx divided by Rx. So that means Thevenin impedance looking into this circuit is simply going to be Rx, and this is not an inductor. So Antonio circuit cannot be used to substitute floating inductor. It can be used only for grounded inductor. So, but anyway, for the low pass circuit, we have already seen that Sallen-Key circuit is a low pass circuit of second order and active type, which gives certain gain also. So one can, in fact, one will always go with the Sallen-Key topology for second order low pass implementation. But anyway, if someone wants to use this Antonio topology or circuit also to implement a low pass filter, then that is also possible. So in that case, what one will have to do is one will have to take Z1 as capacitor, Z2 resistor, and Z3 will now be modified by parallel of resistor and capacitor, and Z4 is resistor, Z5 is resistor. So in this case, what one can do is find out Z in here, and in this case Z in turns out to be of this type, right? So we take that circuit, and from that circuit we create this new circuit. So this is what we have already studied in the previous slide, this one. So we take this whole thing and connect here, and take input and another register and take the output from here, right? So when this circuit is completely implemented using this modification of Antonio topology, then you see that we are taking output from here, not from some other point. And in this case, one will be able to implement a second order low pass filter. So here the output will be now given by this expression Zin divided by Zin plus R1, and when we substitute Zin by this expression, which is 1 by Cs into Rx Cs plus 1, so what one will get finally here is second order filter transfer function. But in this case, gain, however, is going to be equal to 1. So if someone wants gain also, one will have to go for the Sallen-Key implementation. So references for this lecture are Behzad Rajavi, and this Antonio circuit is discussed in Sidra Smith also, and the first order filter circuits, they were taken from this op amps for everyone by Bruce Carter and Ron Mancini. We will use this book in future classes also.